Hello and welcome to this video for Mechanics of Deformable Solids. We are still in Chapter 7, Bending. So what we saw in the previous video is when you have a beam subjected to a bending deformation, there is two types of internal actions that will matter. The first thing is if you have a beam and you cut it at a given position, then the first thing that you can have is that there will be an internal moment. That will be the moment that is applied by the right part of the beam to the left, or by the left part of the beam to the right. And in this case, this internal moment at a given position is going to be characterized by the internal moment of the beam. And we are going to define this internal moment of the beam with the following sign convention, where the moment is anti-clockwise if it's applied on the right surface of the beam at this position, or clockwise if it's applied on a left surface like this. So that is the first thing, that is the internal moment. The second thing that will matter is the internal shear. So again, this will be the shear that is applied by the left to the right or the right to the left. And in this case, if you cut the beam into two parts, we are going to define the internal shear as going down if it's applied on the right surface, or going up if it's applied on a left surface like this. So now to calculate this internal moment or internal shear for every position X within the beam, you can always apply the method of sections. That's always going to work, but there are some methods that are faster to calculate the evolution of the internal moment and the internal shear as a function of X. And one of these methods is the integration method. And that's what we are going to do in this video, is to derive the foundation behind this integration methods. So to derive this integration method, what we are going to do is to consider a very general case. So where you have a beam like this along a given axis X, and this beam can be attached to some supports, so some pins, some rollers, etc. Then the second thing is that this beam can also be subjected to some distributed load. So you can have a distributed load W that depends on X. And in addition to that, you can have some concentrated forces. So you can have some concentrated forces, shear forces that are at a given position like this, or you can also have some concentrated moments like this. So some moments that are applied at a given point. And so what we want to do in this method is to convert what we know. So what we know in this case are the external forces. So we know the distributed load, W, that's an external forces. We would know the concentrated force, and we would know the concentrated moments like this, to what we don't know. So what is unknown? So what is unknown will be first the internal moment and the internal shear. Those are the internal forces acting within the beam, and those are the ones that we want to calculate. So now what we are going to do is to see several cases of different potential combination of when you have a load, when you have some concentrated force, when you have a concentrated moment, or when you have nothing. And we want to see for each of those cases, how can we calculate the internal shear and the internal moment. So the first case that we are going to see first is the most simple case, which is the case where there is no force that are applied at a given point. So in this case, we consider a given point X naught, and let's assume that at this point X naught, so not only there is no concentrated forces, there is no concentrated moment, but we are going to assume that at this point there is also no distributed moment. So W would be equal to 0 at this point. So there would be no concentrated force, no concentrated moment, and there would be no distributed load as well. So in this case, what we are going to do to see what happens to the internal shear and the internal moment at this point is that we are going to isolate around this point a very thin portion of the beam. And so if we zoom on this beam, so we would have at a given point x naught, so we isolate a very infinitely thin portion of the beam, and we are going to compare what happens on the right of this position and on the left of this position. So if you consider this as a function, so you have the function of the moment that depends on x and the function of the shear that depends on x, the function m of x and v of x. What we want to know in this case is what happened to the function when you look at it slightly from the right. So if you look at its value at the position x naught slightly from the right, and we are going to call this x naught plus, and what happened to the function when you look at it slightly from the left, and we are going to call this x naught minus, which is what happened at this position x naught when you come either from the left or from the right. So in this case, let's define the internal shears and the internal moment. So we're going to define this with the positive sign convention. So we are going to define the internal shear as going down when it's on the right. So that would be the internal shear at x naught plus, and the internal shear is going up if it's applied on the left surface like this. So that would be the internal shear at x naught minus. And then we are also going to define the internal moment. So the internal moment is always positive when it tends to make the beam smile like this. So that would be the internal moment at x naught plus and the internal moment at x naught minus. And so now what we are going to do is to write the condition of equilibrium to find the relationship between the shear on the left and the shear on the right, moment on the left, moment on the right. So if we write the condition of equilibrium, so in this case there is no force along the x-axis, so we are going to first write the fact that the sum of the projection of the forces along the y-axis is 0. So in this case we have two forces along the y-axis. We have v x naught minus, which has a positive projection along the y-axis, and we have v x naught plus that has a negative projection on the y-axis. The sum of those two forces is equal to 0. So we find that in this case the internal shear on the right is going to be equal to the internal shear on the left. So that's the first thing. The second thing we can write is now the fact that the moment, the sum of the projection of the moment have to be equal to 0. So in this case, what do we have? We have the moment on the right. This one has a positive projection. So the moment on the right is the moment at x naught plus. And we have the moment on the left, the moment at x naught minus, which has a negative projection. The sum of those two projection of moment is equal to 0. So we find that the moment on the left is equal to the moment on the right. So what does this tell us? So in this case, we find that if there is no forces that are applied, then what we find is that the moment on the left is equal to the moment on the right, and the shear on the left is equal to the shear on the right. So what it means is that in this case, if there is no concentrated force or no concentrated moment at this point, then what we will find is that the internal shear and the internal moments are some continuous function. So what does it mean to be a continuous function? It means that in the mathematical sense, the value of the function coming from the left is equal to the value of the function coming from the right, which means that there is no discontinuity in the internal shear and the internal moment. This is only true when there is no concentrated force or no concentrated moment. So we will see the case of when there is a concentrated force and when there is a concentrated moment next. But the first thing that we can write first is that if you have at a given position no forces and no moments that are applied, then the internal shear and the internal moment will be a continuous function, which means that the shear on the left will be equal to the shear on the right, moment on the left will be equal to moment on the right. So now let's consider the second case, which is the case where there is a distributed load. So we are going to consider that we are still at a position where there is no concentrated force or no concentrated moment, but there is a distributed load W that is not zero. So in this case, the premise that the distributed load W of x is something that depends on x. So if we want to derive an expression that relates the distributed load to the internal shear and the internal moment, then what we need to do is to isolate a very small section of the beam so that we can consider that this section is so small that the internal load W of x will not vary too much within this section, so that we can assume it's constant. So what we are going to do is to isolate a portion of the beam between x and x plus dx. So if I zoom on this, it means that this is going to be the beam going between x to x plus dx. And so we will have in this case a distributed load W of x that is going to be applied in this case on the top surface of this beam. So in this case, remember that the distributed load W is a load per unit of length. So in this case, the force, if I isolate a very small portion of beam of length dx between x and x plus dx, the force that will be associated to this distributed load will be the distributed load times the length over which it is applied. So in this case, first we assume that the distributed load between x and x plus dx, dx being so small, we assume that the distributed load W will be constant and will just be equal to W of x, the value of the distributed load at x. And that's going to be something we assume to be constant. And so to get the force, we need to multiply the distributed load by the distance over which it is applied. And in this case, the distance is dx. That's the length of the beam. So now, based on this, so what we're going to do is, again, define the internal shear and the internal moment. So in this case, that's going to be the shear on the right. That's going to be the internal shear at x plus dx going down due to the sign convention. And now we have the internal shear at the position x that is going to be going up due to the sign convention. And we're going to do the same for the internal moment. Again, the internal moment is always positive when it makes the beam smiles. That's going to be the internal moment at x plus dx. And that is the internal moment at x. And so now let's define a given point O here, for example. And again, we are going to write the condition of equilibrium to find the relationship between the moment on the left and the moment on the right, and the shear on the left and the shear on the right. So let's start by the fact that the sum of the forces along the y-axis has to be equal to 0. So in this case, what we have is we have the internal shear at x going up, so positive sign, positive projection. Then we have the internal shear at x plus dx. That is, in this case, going down. So the projection is negative in this case. Remember that in this case, we define the internal shear as going up on the left, going down on the right. That's the positive sign convention for the internal shear. Necessarily, one must be going up and the other one must be going down for the beam to be at equilibrium. But the sign of the internal shear doesn't tell you anything about the projection of those forces. In this case, the force at x is going up, so it has a positive projection once you write the condition of equilibrium, and the internal shear on the right has a negative projection. So the sign of the internal shear is not the same as the sign of the projection of those forces. And in this case here, as compared to the previous case, we also have the force that is associated to the distributed load, so W times dx, and those are the only vertical forces. So here, so what we have now is we can write that the distributed load W of x at the point x, we can write it as the internal shear at x plus dx minus the internal shear at x divided by dx. And so what this means is that if dx is very small, if dx is an infinitely small distance, if dx tends towards 0, then what we have here is the definition of the derivative. The derivative of the function v with respect to x is equal to the increment of the function along the y-axis divided by the increment of the function along the x-axis, which is exactly the value of the function at x plus dx minus the value of the function at x divided by dx. So what we find here is that the distributed load is equal to the derivative of the internal shear. So that's a very important relationship, is that in this case, when there is a distributed load and when there is no concentrated load or no concentrated moment, the shear, the distributed load W will be the derivative of the internal shear, which means that on the other hand, the internal shear will be the integral of the distributed load. So that's going to be a very important relationship that we are going to use to calculate the internal shear in terms of the distributed load. So now let's consider the other cases, which is the fact that the sum of the moment about a given point is equal to 0. And so in this case, what we have is the moment at x plus dx, which has a positive projection. So that's going to be what it is. Then we have the moment at x, which has in this case a negative projection. So then we have the moment that is associated to the distributed load. So in this case, the moment would be a negative moment. So we would have the arm of the force that would be dx over 2 times the value of the force, which would be wx times dx. So that would be the moment that is associated to the distributed load. And then we have the moment that is associated to the internal shear. So the internal shear at x plus dx, its line of action is going through the point O, so I can neglect this one. This one would have a 0 moment about O. But then we have the moment created by Vx. So this moment is going to create, this force Vx is going to create a negative moment. And the arm of the force is dx. And so the sum of those moments is equal to 0. So here when we look at this, so we have several terms. Some are very small and some are even smaller than others. So in this case, we need to look at the order of those different forces to see if some of them can be neglected. For example, here we have a term which is V times dx. So in this case, this is a term that is of the first order in dx. So if dx is very small, then V times dx is going to be very small too, and it's going to be proportional to dx. So if dx is very small, the term V times dx is going to be a first order of dx. But then we have this term here, the W times dx square, which is going to be a second order of dx. It's going to be proportional to dx square. So if dx is very small, dx square is going to be even smaller. And in this case, since this term is a second order of dx, is going to be infinitely smaller. So in this case, we can neglect it because it's going to be so small as compared to the term that is a first order of dx. So I'm going to get rid of the term that is proportional to dx squared because it's a second order of dx. So then based on this, what I can write is that the internal shear V of x is equal to the internal moment at x plus dx minus the internal moment at x divided by dx. And what this means, again, we see here the definition of the derivative, but this time it's the derivative of the internal moment. So what we find by this is that now we find another very important relationship, which is that the internal shear is equal at a given point to the derivative of the internal moment. So that's a second important relationship. It means that the shear is going to be the derivative of the moment, but it also means that if you know the moment, you can get the shear by integrating the moment with respect to x. So that's going to be a very important relationship again to calculate the internal shear and the internal moment within the beam. So now let's consider the third case, which is the case where you have at a given point a concentrated shear force. So in this case now we are going to consider the case where at a given point x naught you have a concentrated shear force F naught like this. So what we are going to do to see the effect of this shear force is where we are going to do the same thing that we did before in the case where there was no force at all, is that we are going to zoom in on the portion of the beam that is slightly before and slightly after x naught. In this case, we don't need to take a portion of size dx because there is no internal load in this case. We are going to focus on the case of the concentrated shear force. Again, I'm going to define first the external force that is being applied. So now we have an external force F naught that is applied at this point specifically. And let's define the internal shear. So same thing, internal shear at x plus, internal shear at x naught minus. So this is the internal shear slightly before and slightly after x naught. And same thing, the moment. Moment is defined to be positive like this. That is the moment at x naught plus, moment at x naught minus. Same thing, we are going to now write the condition of equilibrium. So let's start by the fact that the sum of the moment is equal to 0. So sum of the moment about a given point is equal to 0. In this case, the only moment are still the moment at x naught plus and the moment at x naught minus. So in this case, we find that the moment at x naught plus is equal to the moment at x naught minus. So exactly the same relationship as before. It means that in this case, when there is a concentrated force, the moment is still a continuous function. So the concentrated force does not affect the continuity of the moment. So the moment, just like when there is no force at all, the moment is a continuous function of x, which means that the moment is the same on the left and on the right. So now let's look now at the sum of the forces along the y-axis, the sum of the projection of the forces along the y-axis. So what do we have? We have the concentrated shear on the left, which has a positive projection, concentrated shear on the right, which has a negative projection since it's going downwards. And we have the concentrated force F naught. Some of the forces must be balanced. So what we find now is that if I write the difference between the concentrated shear on the right minus the concentrated shear on the left, this is the quantity that I'm going to write delta V. This is the difference between the concentrated shear. This is the difference between the internal shear on the right and the internal shear on the left. I'm going to write it delta V at x naught. And if I look at the previous relationship that I got, the difference between the internal shear on the right minus the internal shear on the left is going to be equal to plus F naught. So in this case, this is another important relationship. In this case, what we find is that the internal shear on the right at x naught plus is not the same as the internal shear on the left at x naught minus. It means that in this case, there is a discontinuity. There's a discontinuity in this function. So in the same sense that in mathematics, when you have a function that is discontinuous, the value of this function is not the same at a given point, depending on whether you come from the left or from the right. So what we find here is that when you have a concentrated shear force, the internal shear will be discontinuous at the point where the concentrated shear force is applied. And in this case, the second thing is that the value of this discontinuity, the jump in the concentrated in the internal shear at this point will be equal to the value of the concentrated force F naught. So if we want to represent this, it means that if you plot the function of the internal shear at the specific point x naught, so this is going to be the value of the internal shear can have any trend before that. All we know is that at this point x naught there will be a discontinuity. The internal shear will be either suddenly increasing or suddenly decreasing. And what we know is that the value of the discontinuity is equal to plus F naught. So if you have a concentrated force F naught at a given point, this is going to induce a discontinuity in this function, and the value of the discontinuity, the value of the jump, is equal to the concentrated force F naught. Now, case 4. Next case, we're going to consider the case now where you have, so similar idea, but this time you have a concentrated moment at the point x naught. So this time you are the case where at x naught you have a concentrated moment m naught. So at this point x naught. So same thing, let's start with the fact that the sum of the forces along y is equal to 0. So in this case, the only forces along y will be the internal shear on the left and internal shear on the right. So in this case, we find that the internal shear on the right will be equal to the internal shear on the left, since the sum of those two is equal to 0, and one has a positive projection, one has a negative projection. So in this case, it means that if there is a concentrated shear force, then the internal shear is going to be discontinuous. But in this case, if there is no concentrated shear force, if there is just a concentrated moment, then we still find that the internal shear is the same on the left and on the right, which means that it's a continuous function. So the internal shear will only be discontinuous when there is a concentrated shear force at a given point. So now let's write the fact that the sum of the moment is equal to 0. So what do we have in this case? We have the moment on the right, which has a positive sign projection. That's the moment at x naught plus. Then we have the moment on the left, which has a negative projection. That's the moment at x naught minus. And we have the moment at x naught, which is, in this case, has a positive sign, positive projection. And the sum of those moments is equal to 0. So same thing here. I'm going to now write the difference between the moment on the right and the moment on the left. So the moment on the right minus the moment on the left. This is what I'm going to call delta m. The difference between the moment on the right and the moment on the left. And in this case, if I look at the previous expression, the moment on the right minus the moment on the left is going to be equal to minus m naught. So that is another important relationship. In this case, it means that the moment on the left is not the same as the moment on the right. So same thing as before, it means that the function is going to be discontinuous. So if you have a concentrated moment at a given point, that is going to induce a discontinuity in the internal moment. In this case, the value of the discontinuity is going to be equal to minus m naught. So in this case, one thing to remember is that if you have a concentrated moment m naught at a given point, if this moment has a positive projection, if it's an anti-clockwise moment, then this moment is going to induce a discontinuity, but this discontinuity is going to be negative. It's going to be equal to minus m naught. So in this case, if I plot the moment as a function of x, so in this case, I mean that the moment can have any value, but at this point x naught, there will be a discontinuity, and the value of the discontinuity is minus m naught. So you will have a discontinuity in this function. The value of the moment at x naught will be different whether you come from the left or from the right, and the value of the discontinuity, the difference between the left minus the right, is going to be equal to minus m naught. So in this case, unlike the case of the concentrated shear force, there is a minus sign here, which means that a positive concentrated moment is going to induce a negative discontinuity and vice versa. And finally, we are going to see case 5, the last case that we are going to see. And this time we are going to focus on what happened at the edges. So the edges would be the right or the left extremity of the beam. And in this case, this is what we will call the limit condition. The limit condition are the value of the function, the value of the internal shear and the internal moment at the two extremities, the right extremity and the left extremity of the beam. So let's consider the two cases. Let's consider the case of, on the one hand, the left extremity of the beam. So that would be the point A here, and also the case of the right extremity of the beam, which would be the point B. And so we're going to consider a general case, not necessarily the case that I draw here, where so you isolate the left extremity of the beam, and that's, for example, going to be at x equals 0 at the point A. And in general, this beam at the position A can be subjected to some external forces. So for example, if the beam is attached to a pin at the point A, then you will have a concentrated shear force that is applied. But potentially, if this beam is attached to a fixed support, then you may also have a concentrated moment that is applied at the point A. Like if it's attached to a fixed support, the fixed support may apply a moment at the point A. So in this case, what I'm going to assume is that there's going to be a shear force that I'm going to write VA, and a moment that I'm going to write MA that are applied to the beam at the point A. So in this case, I'm going to define those shear force, and in this case, I'm going to write them with the positive sign convention for the internal shear and the internal moment. Usually when we define the unknowns, we don't need to worry about the sign, about the way we derive them, because those are unknown. But in this case, for the sake of this proof here, I'm going to write them directly with the sign convention that we use for the internal shear and the internal moment, and we will see in a few seconds why. So I'm going to assume that in this case, there might be potentially an internal shear, an external shear VA that is applied, for example, by a support at the point A, and there might be also a moment. And now, so I'm going to look at what happens on this beam if I look at it slightly from the right. So if I look at what happens slightly from the right, so at 0 plus, if I look at the value of the internal shear and internal moment at x equals 0, but this time coming from the right, so I'm going to do the same, define the internal shear at 0 plus and the internal moment at 0 plus. And what I want to know here is what is the relationship between the external forces and external moment that are applied at the edges and the value of the internal shear and internal moment in the beam. So let's do this. So again, we are going to write the condition of equilibrium. So in this case, if we look at the sum of the forces along y is equal to 0. In this case, we find that there is only two forces that are vertical, VA going up and V naught going down. So necessarily those two forces must be balanced. So in this case, what we find is that the internal shear at 0 minus is going to be equal to VA. And if we do the same and write the fact that the sum of the moment about a given point is equal to 0, again, here there is only two moments, and so the internal moment has a positive projection and the moment A has a negative projection. So what we find here is that those two moments must be balanced, which gives you that the moment at 0 plus is going to be equal to MA. So that's what we find for the left extremity. Let's do the same for the right extremity now. So now this time I isolate the part of the beam that up to the point B. For example, it can be, let's say, at x equal L, but this doesn't really matter. Same thing, I'm going to define some arbitrary concentrated shear and concentrated moment that are now applied on the right. And so I'm going to write them with the sign convention that you would expect for the internal shear and internal moment. So potentially at the point B, you may have a shear force, and this time I'm going to write it going down because that's the sign convention we expect for the internal shear. And you can also expect a concentrated moment, for example, if the beam is attached to a fixed support at the point B. And this time I'm going to write it anti-clockwise because this is the sign convention that we expect for the internal moment. And so same thing, I'm going to define now what happens inside the beam at the point L, but coming slightly from the left. So same thing, I will have the internal moment. That's going to be the moment at L minus, at the point L, but coming from the left. And you have the moment at L minus. So you have the shear at L minus and the moment at L minus. Same thing, condition of equilibrium. Some of the forces along the y-axis is equal to 0. Very similar here. You find that in this case, the internal shear at L minus is equal to VB, and the internal moment, if you write the fact that the sum of the moment is equal to 0, you would find that the moment at L minus is equal to the moment at B. So we find those two relationships. What do they mean? It means that in this case, if you are at the extremity of the beam, and this is only going to be valid at the extremity, the left and the right extremity, then we find that provided that we write the unknown forces, like the reaction support, with the positive sign convention that we use for the internal shear and the internal moment, then at the extremities, the internal shear and the internal moment become equal to the external shear and external moment that are applied on the edges. So that is, again, something that is going to be only valid at the edges. In general, at a given point inside the beam, there is no reason that the internal shear would become equal to the external shear. The only thing we know is that if you are inside the beam at a given point, if there is an external shear that is applied, an external shear force F naught, that doesn't mean that the internal shear force is equal to F naught. The only thing we know is that if there is an external shear force, that is going to induce a discontinuity in the internal shear force. But now what we see is that when you are at the edges, at the extremity, and that's only valid at the extremities, then the internal shear and the internal moment become equal to the external shear or the external moment. Again, only valid at the extremities. At the extremities, so that's what we call the limit condition, it's only valid at the extremities. The internal shear and moment become equal to the external shear and external moment, equal to the external shear and moment. So that's an important relationship again, because it tells you what happened at the edges. So again, the important thing is that here, when you are at the extremities, the internal shear and internal moment become equal to the external shear and external moment. So in this case, that's the only thing, the only places where the internal shear and internal moment will become equal to the external shear and external moment. That's only valid at the extremities, but it's going to be a useful relationship because it means that if you first calculate the value of the unknowns at the two extremities, if you calculate the value of the shear and of the moment that are applied by the support at the two extremities of the beam, then it means that that tells you the value of the internal shear and the internal moment at those 2 points. On the other hand, what it also means is that if you have a free extremity, so just an extremity like this or like this, which is not attached to a support, and if there is no external load and external moment applied at this point, then necessarily, since there is no external load, no external moment at this point, then it means that in this case, if you have a free extremity like this, then since there is no external load and external moment, and since the internal load and internal shear and internal moment become equal to the external shear and external moment, since those external shear and external moment are equal to 0, then necessarily it means that at this point the internal shear and the internal moment, they will be both equal to 0 only at this point, So this is only going to be the case when you have a free extremity. So if you have a free extremity with no external shear or no external moment, then at this point necessarily the internal shear and the internal moment will be equal to 0. So if we summarize what we have seen that first, if you have a distributed load W at a given point X, then the distributed load is going to be equal to the derivative of the shear at this point. So the distributed load is equal to the derivative of the internal shear. So it means that if you think about this geometrically, the distributed load W is going to be equal to the slope of the internal shear. So the derivative of the internal shear or the slope of the internal shear. It means that on the other hand, what you typically know is the internal load, and what you want to know is the internal shear. So what you want when you know is the distributed load W, and what you want to know is the internal shear V. So in this case, what this tells you is that you can get the internal shear V by integration. Since the distributed load is the derivative of the shear, then it means that the internal shear is going to be the integral of the distributed load. So in this case, remember the sign convention matters. So for the distributed load, what we call a positive distributed load is a load that has a positive projection. So that's a load that goes up. And for the internal shear, this is the positive sign convention for the shear. So in this case, it means that if you know the distributed load, and you always know the distributed load because this is a known force, a force that is given, then you can integrate it to get the internal shear. So now the second thing we have seen is that the internal shear is the derivative of the moment with respect to x, which means on the other hand that now we know that we can calculate already the internal shear V by integrating the distributed load. So now what we will want to find is the internal moment. So if the shear is the derivative of the moment, it means that the moment is going to be equal to the integral of the shear. And again, here what matters is also the sign convention. So the sign convention for the internal moment is like this. So here what we find is that if you know the distributed load, then by integration you will be able to calculate the internal shear, and if you know the internal shear, then by integration you will be able to calculate the moment by integrating the shear. So here in this case, it means that to get the shear and the moment, we will need to do two integration of the load. We need to integrate the distributed load one time to get the internal shear, and then a second time to get the internal moment. So when you do an integration, you get an integration constant. Why? Because if I know that the load is the derivative of the shear, if I take the derivative of the shear, if I take the same shear plus a constant, it's still going to have the same derivative. So if I know only that the load is the derivative of the shear, that means that the shear is the integral of the load. I'm still missing an integration constant. I need to find an integration constant. And the way you're going to find those constants is by using the other relationship that we have seen. The first one that we have seen are the limit condition, LC, the limit condition. And the limit condition tell you that V and M become equal to the external shear and forces at the extremity. So internal shear and the internal shear and internal moment become equal to the external shear and external moment at the extremities. So if you calculate the value of the external forces and external moment at the extremities, which we call the limit condition, then that is going to give you some integration constants. That's going to give you some relationship that you can use to find the value of those integration constant. And another case that can also be useful are the other equation that we saw when there is a concentrated force or concentrated moment. Again, those are going to be some conditions that can allow you to calculate the value of the integration constant. The first thing that we saw is that if there is a concentrated shear force at a given point that is going to induce a discontinuity in the internal shear, and if there is a concentrated moment at a given point, then that's going to give you also a discontinuity in the moment. So that's, in this case, that's a case where you have a concentrated shear force like this at a point x naught, or when you have a concentrated moment at x naught like this, that is going to induce a discontinuity in the internal shear or the internal moment. So in this case, those three relationships here, the limit condition and the discontinuity, will allow you to find the integration constant that you will get, that you will need to get when you integrate the load. So in this case, when you face a bending problem and you want to calculate the internal shear and the internal load by using the integration method, the method will be as follows. So the different step will be as follows. So the beginning will still be the same. The first step will always be to draw the free body diagram and to identify the known force, the external forces, both the concentrated load, the concentrated shear, the concentrated moment, and the distributed load W. So here you need to identify all the concentrated shear force, all the concentrated moment, and also all the distributed load. So all the external forces that are applied to your system. Then second thing, step 2, this doesn't change. You need to identify the unknown. So this is still the same. You need to identify all the supports and identify how many unknowns you have. So this is still the same. Step 3, you need to use the condition of equilibrium to calculate the unknown. So that is going to be that is always important, but in this case that's going to be even more important because you will need those unknowns. You will need to know the value of the external forces that are applied at the two edges of the beam to find the integration constant. Then, so step 4 in this case, so now you will need to find all the values that you will need to find the integration constants. So the first thing that you should look at in this case is there any discontinuity? So in this case, you need to look at, is there any concentrated force or concentrated moment inside the beam? If there is, then we know that this is going to induce some discontinuities in the internal shear and the internal moment. So the first thing in this case would be to look, is there any discontinuity? And if there is, then we know that the value of the discontinuity will be equal to the value of the concentrated force or the concentrated moment will be equal to the discontinuity of the internal shear or of the internal moment. So once you have identified the discontinuities, then you will need to identify the limit conditions. So again, this is due to the fact that we know that at the edges, at the two extremities, the internal shear and internal moment will become equal to the external shear and external moment. Remember that for this to work, the external shear and external moment on the left or on the right must be expressed with the same sign convention as the one you expect for the internal shear and internal moment. So provided that the external shear and external moment that are applied on the two extremities of the beam are provided with the right sign convention, then you can write that the internal shear and internal moment at the two edges is going to be equal to the external shear and external moment. And if the external shear and external moment is not provided with the right sign convention, then you will need to add a minus sign. So we will see some example of this when we talk about some application problem. But here, so step 5, you will need to identify what are the value of the external forces and external moments at the two edges. That is going to give you some constraints for the value of the internal shear and internal moment at the two edges, which is going to give you some equation to calculate the integration constants. Then once you have this, once you have the discontinuity and once you have the limit condition, so typically the discontinuity, that's going to give you something that at, for example, a given point, you have a discontinuity in the internal shear that is equal to F naught, or maybe you will have a discontinuity at a given point in the moment. So you will need in this case to calculate what will be the value of the discontinuity. And in the case of the limit condition, typically that's going to be what you will get is the value of the internal shear on the left, the value of the internal shear on the right. So for example, at x equal L, or maybe 2L or 3L, whatever is the value, the position of the beam on the right. And you will also get the value of the internal moment on the right and on the left. That's what the limit condition will look like. Once you have this, then you will now calculate the internal shear V as the integral of the distributed load. So you will take the distributed load, you will integrate it to find the shear. So that's going to give you one integration constant. So if you integrate the load to get the shear, you will get one integration constant, and you will find the value of the integration constant by using either the discontinuity or the limit condition. And once you have this, it means that now you have an expression for the internal shear. So now you can calculate the internal moment. So you can calculate the internal moment m of x by now integrating the shear, which you just calculated. That's going to give you a second integration constant. And now you will be able to find the value of the integration constant, again, by using either some discontinuity or the limit condition. So once you have done this, what you will get at the end is what you were looking for. That is to say, the value of the internal shear as a function of x and the value of the internal moment as a function of x.